Welcome back everyone. Today we learn about waves. Let us dive in with the definition of a wave. A wave provides a mechanism for the transfer of energy without a physical movement of matter. In this chapter, we will discuss two types of waves, transverse and longitudinal waves. In a transverse wave, the particle oscillates perpendicular to the direction of travel of the wave. This can be further explained by the diagram shown. Notice that even if there is a transfer in energy, the particles vibrate up and down, and do not move along with the wave. A transverse wave may not require a medium for propagation. Here are some examples of transverse waves. Water waves. A spring vibrating perpendicular to the wave propagation. And electromagnetic waves such as visible light and ultraviolet light. In contrast, in a longitudinal wave, the particles oscillate parallel to the direction of travel of the wave. Similarly, the energy of the wave travels, but the particles do not move along with the wave. The particles require a medium to propagate, such as a wall, or a fluid like water or air. This is why light can travel in space, but sound is not able to, as space is mostly a vacuum with no medium for sound to travel on. In a longitudinal wave, it exists as a pattern of compression and rarefaction regions. Compression regions occur when particles cluster in a region and create a pressure above the normal atmospheric pressure, whereas rarefaction regions occur when particles disperse in a region and create a pressure below the normal atmospheric pressure. Examples of longitudinal waves include sound waves, a spring vibrating parallel to motion, and ultrasound waves. Here is a summary of what we have so far between transverse and longitudinal waves. Before we continue, let us learn a few terms in this chapter. The crosses show the equilibrium position of the particles. Take a look at this particle. The crest is the point where the particle is at its maximum positive displacement. The trough is the point where the particle is at its maximum negative displacement. The amplitude is the maximum displacement of a particle from the particle's equilibrium position in a wave. This can be demonstrated in the diagrams below. Theoretically, it is the height of a crest or depth of the trough from the particle's undisturbed level. The wavelength is the distance between two identical points on successive waves of the same phase. From the diagram below, we measure the distance between the two nearest particles at the trough or the two nearest particles at the crest. Before we move on, let us focus on particles A, B, and C. Observe particles A, B, and C, which are part of a wave. When we say that two particles are in phase, we are saying that both particles obey the following conditions. They move in the same direction, have the same speed and same displacement from their rest positions. In theory, we can say that particles A and C are in phase with each other as they move in the same direction, speed, and have the same displacement from their rest positions. Particles A and B are not in phase as they move in opposite directions. However, we can state that they are out of phase with each other. For a transverse wave, it is the distance between two successive crests or troughs. As for longitudinal waves, we find the wavelength by measuring the distance between two particles at phase with each other. Next, we have the period, which is the time taken to generate one complete cycle of the particle. To demonstrate, we have a particle vibrating as shown. We should measure the time taken as the particle travels this way, or when the particle travels this way. In both situations, represent one cycle. A common misconception that students make is to measure the time taken as shown. This is wrong, as this is not a complete cycle, but rather half of a cycle. We should also take note as the amplitude is not the same as the period, as amplitude is a length while the period is the time taken. Using these three quantities, we can construct two types of graphs. displacement of the particle along the wave against the position of particle from the origin of wave source, and displacement of the particle along with the wave against time. First, we have a graph of displacement of a particle against the position of the particle from the source of the origin. We can obtain two important information about the wave. The amplitude of the wave is measured from the x-axis or midline, and the wavelength by measuring the distance between the two nearest points in the same phase between each other. Next, we have a graph of displacement of a particle against time. We can obtain two important information about the wave. The amplitude of the wave is measured from the x-axis or midline, and the period by measuring the distance between the two nearest points in the same phase as each other. Now, let us introduce more terms. The frequency is the number of crests or troughs that pass through a point per second, or the number of waves generated per second. It uses Hertz as an SI unit. 1 Hertz is equivalent to 1 cycle or oscillation completed in a second. We can say that the frequency of a wave is 1 over the period of the wave. Next, we have the wave speed. The wave speed is the distance moved by a crest or trough in a unit time. The wave speed can be calculated as the product of the wave's frequency and its wavelength. Lastly, we have the wavefront, which is a line that joins all the peaks or identical points on a wave. Vibrating particles on the same wavefront have the same phase, have the same speed, and are at an equal distance from the source. Here are the definitions of the terms we have learnt so far. Wavefronts move in the direction of travel of the wave. As seen from the images below, the wavefronts are drawn perpendicular to the direction of the wave. Let us talk about the ripple tank experiment. It is a common experiment to use to observe wave patterns and how they interact. The vibrator is connected to spherical dippers that vibrate and form transverse water waves. The frequency of the wave formed is equal to the frequency of the dipper. During the experiment, a white screen is placed under the wave. Shadows cast by the troughs of the waves tend to be darker. As the wave propagates, the particles in the medium vibrate by moving up and down. If we were to place an object like a paper boat in the same position as the highlighted particle, you will notice that the object will also bob up and down and not move further away from the source. Now, let us talk about the reflection of a wave. Look at the diagram as shown. The normal is an imaginary line that is perpendicular to the reflecting surface. We have the angle of incidence, I, which is the angle between the normal and the incident ray. And we have the angle of reflection, R, which is the angle between the reflected ray and the normal. When a wave reflects, you will observe the diagram as shown. It suggests that during reflection, the angle of incidence is equal to the angle of reflection. A reflected wave will have the same wavelengths, frequency, and speed as the incident wave. There will be no change in the distance between wavefronts. However, because the direction of the wave changes, the velocity will change. How do we draw the wavefronts of a reflected wave? Firstly, we use angle of incidence equal angle of reflection to obtain the direction the wave will move. The wavefronts will then be drawn perpendicular to the direction of the wave. What about reflected circular wavefronts? First, identify the source of the wave and its distance from the plane of reflection. Afterward, draw the image of the origin and draw the image of the reflected wave. Here would be what we should get. The waves would also go through refraction. This can be done by placing a glass plate on the tank would make a difference in the depth of the water. Bending of wave direction is involved when the direction of the incident wave is not perpendicular to the glass block. During refraction, as the wave moves from a deep region to a shallow region, the wavelength will decrease as there is a change in depth. The frequency of the wave will become unchanged since there is no change to the frequency of the source. The direction of travel will change if the wave does not travel perpendicular to the boundary. Since wave speed can be calculated with this equation and the wavelength falls, the speed of the wave falls as well.
That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.